So yes, I'm going to talk about generalization of closed unbounded sets. So where does this start out? So the background really is stationary reflection. So this has been studied for a long time. An ordinal kappa of uncountable cofinality reflects stationary sets. F for every S, which is a stationary subset of kappa, there is some alpha less than kappa such that S intersect alpha is stationary in alpha. Okay, so that's the main definition. And then we've got these two main theorems I wrote up here. In L, a regular cardinal reflects stationary sets if it's weakly compact. So that's pi11 indescribable. We'll be coming back to this. And in the theorem of Kuhnen, it is consistent to have a weakly compact cardinal that is not weakly. It is consistent relative to a weakly compact cardinal that a non-weakly compact cardinal reflects stationary sets. Okay, so it doesn't need to be weakly compact. So then there's the recently Bagaria, Magadov, and Sakai came up with a generalization of the notion of stationarity, which is really what my work came out of, based on this notion of reflecting stationary sets. So start out with that. What is it? Okay, we can think of the superstationary, so stationary plus, say, if you at a stationary reflecting cardinal, you can say S subset of kappa is stationary plus if for every stationary set T, there is some alpha which is in S such that T is stationary in alpha. So that's just saying, you know, this S does this stationary reflection. Okay, you can continue to strengthen these notions. They give rise to some interesting things. So you can have alpha stationary sets reflecting all beta stationary sets, or beta less than alpha. So this is very nice, but you may wonder, well, you know, when we normally introduce stationary sets, we say they are the things which intersect every closed unbounded set. So have we got some characterization of these higher order stationary sets in terms of intersecting something like a closed unbounded set? So some generalization of closed unbounded sets. And the answer is yes, we do. This is what I've been working on. This is really where my work starts. Okay, so this definition is going to be an inductive definition in 5 parts, but it's not as scary as that makes it sound. We're going to end up with, closed unbounded being 0 club. So we're going to start out at that. So first we say that S is 0 stationary if it's unbounded. Okay, nice. We're happy with that. Then C is n stationary closed F for any alpha such that C is n stationary in alpha, we have that alpha is in C. So what's 0 stationary closure? Well, that's just closure. That's our ordinary thing. Okay. Then we say that C is n club, so n closed unbounded in kappa, if it is n stationary closed below kappa, and it's also n stationary. So again, let's check. 0 club, well, that's being n 0 stationary closed, so being closed in the ordinary sense, and being 0 stationary, so being unbounded, that's just closed unbounded. So then we need this part 4. You want to go on to saying, well, stationary intersects all n clubs, but we need this part 4. So this is saying that we need, when we talk about the next level of stationarity, we need to make sure we've got an n reflecting property. So kappa is n reflecting if for any pair of n stationary sets S and T, there is some alpha less than kappa with S and T both stationary below alpha. So at the 0 stage, the simplest stage, this makes sense. Because that reduces to being of uncountable cofinality, and we need to talk about stationary sets, we need uncountable cofinality. So this is sort of going to be what we need to get the higher versions. Okay, and then part 5, that's just ordinary stationarity in the going from 0 to 1 case. So S is n plus 1 stationary in kappa, if kappa is n reflecting, I said we needed that, and S intersect C is non-empty for every n club C. So then we can go back to the beginning and talk about 1 stationary. Well, that's stationary, we know about it. 1 stationary closure, and one club. So that's going to be the thing that you might have at a reflecting cardinal. Okay. So one thing to say about 4, that's going to ensure that our n clubs form a filter. That's the sort of thing we want. So there's some notation to introduce here, which is kind of useful. It's useful to think about these things. So this was introduced by Pythagorean, Magador, and Sakai. We say dn of A for some set of ordinals A is the point below which A is n stationary. Okay, so the points where A reflects as an n stationary set too, maybe that's what I'll say. So let's have a look at those definitions again, because those are the really important. This is the really important thing. This definition. We can restate them in terms of this dn of A notation. So 0 stationary and unbounded. We had that before. 2 and 4 that are really we use this for. So n stationary closure. That's just saying dn of C, the points below which C is n stationary, is a subset of C. And then looking at the kappa being n reflecting, that's for any pair of n stationary sets, S and T, we have dn of S intersect dn of T, intersect kappa, we need something below kappa, is non-empty. Okay, so that's our definition of an n club. What can we do with it? Can we do some nice things? Well, hopefully. So firstly, some basic properties. You might want to think about, well, how do these things relate? So if I'm looking at a 1 stationary set, how does that compare to a 2 stationary set? And similarly, if you're at how is a 0 club, how does that compare to a 1 club? Well, we have, if we're at this n reflecting cardinal, which is where we need to be to define these things, and you have m less than n, then n plus 1 stationary implies m stationary. So n plus 1 stationary is the sort of strongest, the biggest set you get, and all of that, so n plus 1 stationary will be, for instance, ordinary stationary. But on the club side, you have m club implies it's n plus 1 club, so the strongest club is the ordinary club, and these clubs get weaker, and we can see that from just thinking about how dense they are. I think I haven't written here that the n clubs are also n plus 1 stationary, but that's fairly obvious because, well, actually, yeah. Okay, so I need to first come on to the n clubs forming a filter, and then we'll get that. Okay, but first, so this is a nice way of getting our n clubs. How do we produce them? Well, if we've got an n reflecting cardinal and S is n stationary, then we just take the points below which S is n stationary, so the points where S reflects to as an n stationary set, and that's going to form an n club. And this is a very useful property. So then there was that thing that I told you earlier, that we wanted these n clubs to form a filter, then we can do lots of things. And if we've got kappa n reflecting, then the n club subsets of kappa do generate a filter. So any two n clubs intersect at an n club. And so then you see that the n clubs must indeed be n plus 1 stationary. So how do these things, are these things the same as the superstationary sets introduced by Pythagorean, Magador, and Sakai? Well, they are. In this sense, we've got that these sets are where stationary sets are reflected to. So if kappa is n reflecting and you have some subset of kappa, then if it's n plus 1 stationary, f and only f, for any n stationary set, in kappa we have that A is reflected in S. So dn of A intersect S is non-empty. So this is actually quite easy to see from what we have above. If S is n plus 1 stationary, then it intersects every n club. That was the definition. And we have just pointer. So just here we have that dn of, thinking about A here, dn of A here is going to be n club. So it's got to intersect S. And going in the other direction, that's also pretty straightforward, because if you had S with this property, think of some n club C. Well, it's n club, so it's n stationary. So we must have dn of C here instead of A intersect S be non-empty, but by definition of being n club, dn of C has to be a subset of C, so C intersect S is non-empty. Okay, so these are the basic properties. What about more difficult properties? What sort of properties do the n club filters have? So one of the really basic questions is it a normal filter, or is it kappa complete or something? And to look at this, I looked at the connection with the pi1n indescribability filter. So n stationarity is a pi1n expressible property. So pi1n indescribable implies n reflecting. Okay, so that's quite easy. In L, we have that kappa is n reflecting if and only if kappa is pi1n indescribable. So these two notions are quite closely connected. That was shown in Bagaria, Magador, and Sky's paper. But in V, we don't have. We only have the easy implication, unfortunately. Okay, so if kappa is pi1n indescribable, so Fn of kappa is the pi1n indescribability filter. And then we get this nice theorem. So if kappa is pi1n indescribable, and we've got the n club filter over kappa, then first Cn is a subset of the Fn. So this means that any n club is in this pi1n indescribability filter. And if n equals 1 or v equals L, then these things are actually the same. So yeah, this is a bit annoying that you only get it in these cases. So what happens when v does not equal L? Can we force to get, say, that the n club filter is not the same as the indescribability filter? And that's something I don't know about. Yeah, so that's an interesting question. But even though we only have this thing, that still gives us the nice result that the n club filter is normal. So that's at this pi1n indescribable. So that's an easy consequence of the normality of Fn, because you think everything in here is in here, so we can take the diagonal intersection and get something which is in the indescribability filter. It's quite easy to show the diagonal intersection of n clubs is going to be n stationary closed, and then it's n stationary because everything in the indescribability filter is n stationary. So you get normality, which is important for trying to prove lots of things. So this is the first really significant result that I looked at. So a more difficult result involving stationary sets. Solovay showed that any stationary subset of a regular cardinal kappa can be split into kappa many disjoint sets. So the obvious question is, can we do this for n stationary subsets? And I've got a partial answer to this. If kappa is pi1n indescribable, then you can do it. So if kappa is pi1n indescribable, then any n plus 1 stationary set can be split into kappa many disjoint n plus 1 stationary sets. So that's pretty nice. We actually get something slightly stronger than this. When you look at the proof, it forms two parts. So firstly, and in fact most difficult, is to show that any n plus 1 stationary set can be split into 2. So that's kind of surprising that this is difficult to show, but it is. So to do this, we can do this when we've just got the kappa completeness of the n club filter. We don't actually need the normality here. And then we can just use a simple tree construction to show that if we've got the n club filter is kappa complete, and we've got the tree property, any n plus 1 stationary set can be split into kappa many disjoint stationary subsets. Stationary sets. Okay. So that was a sort of section about splitting stationary sets. There are some more exotic constructions using stationary sets. So, for instance, diamond and ineffable, they're kind of closely related. So one thing I looked at was whether we could generalize these. And it turns out that in many cases of the results involving these things, so you put in the obvious definitions and you go through the proofs, and because of the nice structure of these n clubs, you can basically just alter the proofs a little bit and you get out what you want. So you get out a lot of the theorems here. So let's look at a few of these. So we say a regular uncountable cardinal kappa is ineffable if whenever we have a function from pairs in kappa into 2, then there's an n stationary set, ineffable n, sorry. This is just the ordinary ineffability is 1 ineffable. So there's an n stationary set, ordinary ineffability would be just a stationary set, x, which so a homogeneous set, f is constant on. Okay, so then this is another theorem just to give us a nice way of characterizing ineffables. So you take a regular uncountable cardinal, kappa is ineffable n in this first sense as a homogeneous set. If whenever you've got some sequence A alpha, alpha less than kappa, such that for all alpha, A alpha is a subset of alpha, then there's some set A, subset of kappa, which is below stationary, an n stationary set. This A intersect alpha is just A alpha. Okay, so you can kind of guess this sequence correctly at an n stationary set using our sumset A. So this is a quite useful characterization of ineffability. I'm going through these a bit quickly, but then there's diamond. We all know about diamond. What about this diamond n kappa? So this is the assertion that there is a sequence S alpha, alpha less than kappa, such that for any S subset of kappa, we have that. Oh yeah, so each S alpha is a subset of alpha. I didn't write that down. We have that the set of alpha less than kappa, such that S alpha is just S intersect alpha, is n stationary in kappa. So this is just the ordinary definition of diamond, and we replace stationary with n stationary. Okay, so diamond's very useful. What sort of things can we get about it? What sort of results can we get? Firstly, F kappa is ineffable n, then you get diamond n. Okay, that's a nice result, and again, that proof just follows the ordinary proof for the case n equals 1. But there are some difficulties. So we know we can get diamond sequences in L, right? In many places, they're all regular cardinals. So can we get diamond n sequences? We want to show this. Diamond n sequences will only make sense where we're at an n stationary regular cardinal, so where sets can be n stationary. So can we get this theorem? Fv equals L and kappa is an n stationary regular cardinal, then diamond n kappa holds. And indeed we can, but we need to do a bit more work in this case than from previously. So for the proof n equals 1, we use this standard device. This definition, I call it a good elementary L lambda kappa sequence. Ooh, missing any. It's very standard, but it doesn't seem to have a name, a standard name anyway. So this is just a continuous increasing sequence of models which are elementary in L lambda, such that each of them have size less than kappa, and they intersect kappa at an ordinal. So when we collapse these models, we get kappa is equal to where n alpha intersects kappa. Okay, so in the standard proof, we use that we can get these good elementary sequences, and they all form a club set. And these models, when we collapse these n alphas, in those we're going to get some L alpha bar, and there you have the L alpha is and knows what club sets are, but we've got a difficulty when we go on to n clubs, because n club, the notion of n club is not absolute. So we need something which shows that we get correctness about n stationary sets. So in fact, n minus 1 stationary sets here we'll need. So we need many of these things to collapse to levels of L, which are n minus 1, which are correct about n minus 1 stationary sets. In fact, they need to be correct about n minus 1 stationary subsets of this ordinal, the ordinal where kappa collapses to. So this is just a definition of n stationary correct. A model is n stationary correct at kappa, f for any s, which is in the power set of kappa intersect m. We have that m thinks s is n stationary in kappa, f and only f, s is n stationary in kappa. So it's just what you would expect. So this is the important lemma. So under the assumption b equals L, we suppose kappa is pi 1 n indescribable, so that is just n reflecting, because we're in L. And we take a good elementary sequence, good elementary L kappa plus kappa sequence, and we want to make sure, this is just, this is quite simple to get an alpha intersect kappa equal to alpha. And then we can get an n club set Cn such that for any alpha in Cn we have that if we look at where n alpha collapses to, then this L nu alpha is n stationary correct for alpha. So kappa is collapsed to alpha. And this enables us, this lemma enables us to go through and prove our theorem that we get diamond n. Okay, so I do have a proof written out here, but I guess we don't have time to go through it. So let's just give a rough idea of how it goes at this beginning bit, really. So what we do is we just list all the, and we don't want to just list the n stationary sets because we need to preserve the lower ones as well. We need to be correct about the lower ones. So we list all the m stationary subsets of kappa that appear in this sequence of n alphas for all m less than or equal to n, and just put the ones occurring at the earlier n alphas first. Okay, so now it's quite clear on a club D we'll have this, the S beta, the sequence A of S beta such that beta is less than alpha, will list all of the less than or equal to n stationary subsets of kappa that are in our n alpha. So, I mean, this lists all of the things in n alpha. Okay, and then what we do is for each S alpha, if it say that it's M alpha stationary, we take this C alpha, which is the points where S alpha reflects as an M alpha stationary set, and this is going to be an M alpha club. That was one of our basic results about these things, and hence it's going to be N club. And remember that N clubs are weaker than the M alpha clubs if M is less than N. Then we can take the diagonal intersection. We're in L, we're at pi 1 n indescribable, so we know that the n club filter is normal, and we get a 1 club now. So then what we want to do is show that this C intersect D is essentially what we want. It's a 1 club. We've got that because C is it's an n club. So C is n club, and D was club. So a club is an n club. So a 0 club here is an n club. So we've got C intersect D is n club, and then we just go through and show that we get what we want. We get this stationary correctness. Yes. So I should probably not go through that, I guess. Okay. So I guess that's most of what I've shown involving these things. You can also generalize a stronger version of diamond and show that it holds in L at non-ineffimals. And then I've got loads of questions, so I only wrote down a few, so everyone can think of more probably. So important, are the results above sharp? So for instance, can we get a non-kappa complete n club filter sometimes? And so what happens at the non-pi1 n indescribables? That's an interesting question. Then there's sort of more techniques so there's a lot of literature about preserving stationary sets. In forcing, that's very important. So what about preserving n stationary sets? What sort of forcings can do that? Another question, is there an interesting generalization of the square principles using n clubs? It's quite easy to define, but I don't know if it would do anything interesting. So yes, that's lots of questions.
So are there any questions?
So you mentioned stronger version of diamond. Is that diamond star, diamond plus, or?
Diamond star, yeah. So yeah, you have things reflecting to a one club, but each of you don't have individual. You have you know what it is.
So, and have you looked at whether one can force diamond star n?
No, I haven't looked at that.
Okay. Any other questions? If not, let's thank the speaker again.